The problem is 3.1.3. The question is to find error bound for the approximation we did in the problem 3.1.1. So here we're going to use the formula we given in the lecture. The original function f is the Lagrange interpolating polynomial plus this residual term. So the residual term is just see here, it's just x minus each of those given points, and here is just the number of points factorial, and here just the nth order derivative of f at a given point, cx. Okay, so the derivative, the order of the derivative here is the same as number of points. So this cx, because that is just a number between those 3 points. Okay, so here now we have this problem. F of x is given by cosine of x. So we need to derive, if you want to estimate the error, we just need to estimate how large this term is. Okay, so f of x is cosine of x, so f prime is sine, negative sine, f double prime is negative cosine, f triple prime is just a sine. So that's why this part is bounded by 1. So nor of this is bounded by 1 because it's just a sine of something. Okay, and then we can estimate this part. So if the point x is not given, so in the previous question actually x is given as 0.45, so you can just plug in and compute the value here because you have everything here. You know the 3 points, and you also know x. You can actually compute this value. But if you're just given a general formula, say ask you to estimate the error of this Lagrange interpolating polynomial over this interval from x0 to x2, then you have to find the maximum value. You have to estimate the maximum value of this polynomial. And if that's the case, what you need to do is just concentrate on this, focus on this polynomial, which I define as g here. Then you take the derivative, set to 0, solve for critical points, and also find the values of this g at these two endpoints, which are just x0 and x2. Then see which one gives you the largest value. And that is the maximum value of this function g, right? Because we know that this function g is continuous and differentiable over that interval, and that is the way to find the maximum. So for the g defined in this way, we can take the derivative, and that's the g prime, and then solve this for x. We know that this is just a quadratic function here, so we just need to use the formula for the roots of quadratic functions, and that is giving us this x, which is just this. Okay, so and then you can plug in the 3 points x0, x1, x2, and you will figure out that the x is equal to, in this case, is going to be equal to this. Okay, so it actually have 2 roots because you have plus minus here, so you're going to have 2 roots. But this root here is outside of a range from x0 to x2. X2 is 0.9. So this is outside of that, so we don't care about that. We only need to worry about this point, and then also notice that the g function actually takes the value 0 at the point x0 and x2 because you actually have these 2 terms here. That is why the maximum value or minimum value can only happen at this point right here. So you can just evaluate there, the g there, and you figure out the g at there, the absolute value of g at that point is actually 0.322. So that's the maximum value of g over the interval 0 to 2, 0 to 0.9. So this is bounded by 0.322. Okay, so now we already figured out this is bounded by 1, that is bounded by 0.322. So altogether, we just know that the distance between the function f and the Lagrange interpolating polynomial over the interval 0 to 0.9 is going to be bounded by this number. Okay, so that is the general bound over the interval. Okay, you can do the same thing for the other function. We're going to have the f of x equals to the square root of 1 plus x. And to repeat the same procedure, notice that right now you have a different estimation for the for this term because the f triple prime for that function over square root of 1 plus x is different. Okay, but the procedure is exactly the same.